discuss about one-dimensional motion in state potential. Here we have considered a state potential. You can see over here is this region 1 and this region 2. Here you can see the barrier at x is equal to 0. Okay, before this barrier the potential is 0, and in the region 2 it's v naught. So now the particle we have considered is moving from the left direction, okay, where the potential is 0. So it reaches this point, okay, where the potential suddenly becomes v naught, and then the potential undergoes a single discontinuous change at the boundary between the two regions. So the potential thus can be defined. You can define the potential as Vx equal to 0 for x less than 0 or less than 0. This is for region 1, and then Vx equal to v naught for x greater than 0. This is for region 2. This is very, very clear. We have an idea about this thing. Okay, now what happens is this, the dual nature of matter indicates that there is always a wave associated with the particle. Now, this wave travels from left to right in region 1. As soon as it reaches, okay, the interface between the two regions, it suffers a discontinuous change in the potential. Now, due to it, a part of the wave is transmitted into the region, and while the rest of it is reflected back into the region. So it's just like a ball you have thrown to the wall, and it's the bouncing back of the ball to the same direction. So the time dependent independent rather Schrodinger equation in one dimension is d square psi by dx square plus 2m by h cross square into e minus v into psi is equal to 0. Now considering the wave equivalent function in two region, we'll take psi 1 in region 1 and psi 2 in region 2. So we can write the equation for the two regions separately, okay, and this could be written as d square psi 1 by dx square plus 2m by h cross square into e psi 1 equal to 0. Okay, here this is for region 1, okay, for region 1, here v is 0 in the region 1, so e minus v, actually it has to be e minus v, but v is 0, so it's a little bit like this. Okay, now putting p1 is equal to under root 2me, we know this relation. Okay, so this is the momentum. We will get again d square psi 1 by dx square plus p1 square by h cross square psi 1 equal to 0. Okay, so this is for region 1, this is equation 1. Similarly for region 2, we can write d square psi 2 by dx square plus 2m h cross square into e minus v naught psi 2 equal to 0. This is for region 2. Again, if we put p2 is equal to under root 2m into e minus v naught, we'll get in region 2 rather. So the equation will be d square psi 2 by dx square plus you'll have to convert this, so it will be p2 square by h cross square into psi 2 equal to 0. This will be equation number 2. Now the general solution for equation 1 and 2 can be written as psi 1 equal to a to the power I p1x by h cross plus b to the power minus I p1 x by h cross. This is equation number 3. Similarly, for the second region, that will be psi 2 equal to a e I p2x by h cross, okay, plus d e to the power minus I p2x by h cross. So this will be equation number 4. Here ABCD is it's a arbitrary constant which has to be determined from the boundary condition. Now equation 3, you can see it has a two term on the right hand side. The first term indicates the existence of a wave traveling along positive x-axis. This is okay, and this represents the incident wave actually. And the second term, okay, it represents a wave traveling along the negative axis, okay, now which has been reflected back into the region 1. Similarly, if we consider if we'll see the second equation here, the region 2 is continuous region, You can see it's a continuous region. So if it is a continuous region, there is no reflected component of wave in this region. Hence the second term, this term here will be 0. So this equation will be modified, and it could be written like psi 2 equal to C into I P2x by H cross. So actually this is the equation, the modified equation in place of equation number 4. Okay. Now it is well known that the wave function psi has a probabilistic interpretation. Now since it represents the particle probability amplitude, hence psi must be finite throughout. Also the energy E and V should also be finite, since infinite energy does not exist in nature. Okay, it follows therefore from equation 1 and 2 that d square psi by dx square must also be finite. So for dx square psi by dx square to be finite in two regions, the first derivative, applying the condition of continuity, we can say the first derivative of psi, that is d psi by dx, it should be continuous at the interface. And also one thing is there, for continuity of d psi by dx, psi must be continuous. Okay, so this will become the boundary condition actually. Okay, hence from the above arguments, what we can do is that d psi 1 by dx is equal to d psi 2 by dx at x equal to 0. Similarly, psi 1 equal to psi 2 at x equal to 0. So this will be equation number 6 and this will be equation number 7. Applying this boundary condition 7, okay, in equation 3, okay, we get A plus B equal to C. So this will be equation number 8 for applying the boundary condition into equation number 6. Okay, let us differentiate equation number 3. So this was our equation number 3, this one. Okay, we differentiate this one. So we'll get d psi 1 by dx equal to I p1 by h cross a e to the power I p1x by h cross minus I p1 h cross b e to the power I, okay, it's p1x by h cross. And also equation number 5, it was d psi 2 by dx equal to I p2 okay by h cross c into e to the power I p2 x by h cross. Now applying the boundary condition 6, we will find I p1 by h cross a minus b equal to I p2 by h cross into c, or a minus b is equal to p2 by p1 into c. So this will be your equation number, say, 9. Now solving equation number 8 and 9, we have two equations. For here we have a plus b is equal to c, and we have a minus b is equal to p2 minus p1 by c, p2 by p1 by c. So solving a by equation 8 and 9, we'll have a is equal to p1 plus p2 by 2p1 into c, and c, or rather, or c will be equal to 2p1, okay, by p1 plus p2 into a. So this will be equation number 10. Likewise for equation number again we will get, to get the value of b, we will write b is equal to p1 minus p2 by p1 plus p2 into a. So this will be equation number 11. So equation 10 and 11, it both represents respectively the amplitude of the transmitted and reflected wave in terms of amplitude A of the incident wave. Here also we can see that B has been expressed in terms of A, and here also we can see that C has been expressed in terms of A. Okay, now using equation 10 and 11, we can now define the term reflection coefficient or reflectivity. So reflection coefficient, okay, R, it will be represented by R, magnitude of reflected current, okay, by magnitude of incident current. So this is R, the reflectivity or reflectance R of the electron. Okay, it is given by this much. Similarly, the transmittivity, okay, the transmittivity or transmittance of the electron is given by T equal to magnitude of transmitted current. transmitted current by magnitude of incident current. Now we can find the coefficient in two possible way, rather when E is greater than V naught and when E is less than V naught. We'll discuss this in the next lecture. Okay, so this is lecture 1 for this particular topic related to this one, that is one-dimensional motion in a state potential. So this is first lecture. Thank you.